Ladies and gentlemen, welcome to another episode of our seminars on artificial intelligence and machine learning. Today, we have the honor of having Vivek Upadhyay with us as the speaker. Vivek is a PhD candidate in the SAIL lab and has been with us since the very beginning. I believe you joined us in 2019,
Yes.
right?
Yes.
Vivek completed his master's in computer science, if I recall correctly, where he worked on a number of research projects, starting from automatic podcast generation, and then leading to natural language processing, specifically information extraction for open source intelligence analysis. And then over the past 2.5, 3 years, Vivek has been a PhD student, primarily working on the brain-computer interfaces project, adversarial stimuli project that my lab is engaged in. But recently, he has pivoted towards large language models, specifically multilinguality in large language models and the robustness and reliability of those models. It's all the hype these days, and Vivek has already made quite a significant progress in that line of research. I'm excited to learn more about it. I hope you are as well. Please welcome Vivek Upadhyay.
Thank you, Dr. White, for the great introduction. Hello, everyone. I'm Vivek Upadhyay. I'm a PhD candidate here. Today, I'm going to give the presentation on the work that we've been doing in regards of large language model. So our paper is on TACO, translation in the chain of thought process to create efficient multilingual instruction-tuned LLMs. Okay, so let's get started. So we all know what large language models are. It's basically a very, very big transformer model, and there are they have been very useful in recent days. You can chat with your models, right? You can ask your model to write the code in the programming language of whatever programming language you want. They can write a code in that. There are specific models that excel in just writing the code. They can also perform complex analysis that it will be, if you want to give it a simple Excel sheet and access to find out the anomalies in them, it's able to do that. So it's getting very, very, very useful to do more and more complex analysis, right? In addition to that, it can also do some creative work. It can write a poem for you. It can generate the content for you. It can tell you the story. It can write a whole story in the given that you give it to the model, right? Context augmentation, and it can generate other creative work as well. So because of these different scenarios, because of these different examples that LLMs can do, we can find LLMs literally everywhere these days. Now, its application domain, it ranges from academia all the way to the industries, and people all around the world started using this, right? But the problem here is that even these models are really great at what they do. They also have some limitation. There are some limitation in the performance of these LLMs. So the very first limitation is the hallucination. This model starts to write down the queries that you give it to them, and after a while, they would start to hallucinate and it starts generating some unfactual content, right? There's also very lack of explainability. Sometimes it's able to explain why it wrote that answer, and sometimes it cannot explain that. There's a limited contextual understanding. It also generates misinformation, harmful content, right? It's very unreliable. Sometimes the queries that you have provided, model can give you a very accurate answer, and at the same time, with a different temperature, it will provide some very unreliable answers. So you cannot completely reliable on these models because of the poor explainability. And one of the important limitation that I want to focus on is the one at the end, the limited understanding of non-English languages. So this is what we're going to focus on today. We're going to talk about multilingual LLMs. So why do we really care about multilingualism in LLMs, right? So one of the reasons is that the languages, they are disappearing. So by the end of this century, there will be 3,000 languages that could disappear. at the rate of 2 languages per week, and that's not good, right? But what we can do is we can use these large language models such as ChatGPT or Bard and utilize them in order to preserve or revitalize those low resources languages. But the problem is these models, they do not perform well as soon as it goes beyond the English language. So if it's a non-English language, this model fails to perform in a good way. So they might work in the high resource language such as Spanish, but it might perform in a very bad way in the low resource language such as Sanskrit or Maithili or Nepalese. So, and because of that, it also prevents many people around the globe, and it restricts their application to just to a few number of groups only, and the people around the world, everyone cannot use these models. So to demo that, so what I did, I started chatting with the ChatGPT in Sanskrit. So I started asking a very first question that why we need to save the language using large language model, right? So it starts its answer over here, and it starts with the Sanskrit. And as soon as it starts, then later on convert that whole thing in Hindi and starts answering in Hindi. So I thought, okay, maybe I'm making some mistakes. So what I did, I just changed the prompt a little bit. So I asked it all the way at the top to please talk to me in Sanskrit only, and I gave it the same question. So after that, also it gave a first paragraph a little bit in Sanskrit, and then again just went back to explaining Hindi. Hindi is a high resource language. It's very popular in India. So it's not trying, it's basically avoiding to answering stuff in Sanskrit. So I thought, okay, maybe I'm doing something wrong. So what I did, I also tweaked the prompt again. So now what I'm going to tell it is basically in Sanskrit, I'm going to tell it that you are my assistant who is very great at speaking in Sanskrit, and all the answer that the model is going to give it to me, it must be in Sanskrit, right? So I'm making sure that it understands what I need from it. So this seems to work, right? So when I give that prompt to the model, I got a very long answer, and I was very happy. All right, this works really great. Maybe that was the only key I needed. I just needed to do some prompt tuning, and it just gives the answer. But when I copy that answer and try to understand back in English, it doesn't actually make sense. It looks like a good answer, but it's not. So in comparison to that, I ask the same question in English, and it gives me in a very nice way all the answer that I require, right? It talks about preserving cultural heritage, linguistic diversity, knowledge transfer, and everything, right? So multilingualism is a very challenging in proprietary models as well, right? Such as Bard, ChatGPT. We just saw the example in ChatGPT. It's not able to perform well in non-English languages, right? But even if these proprietary models such as ChatGPT, it's capable of answering in the Spanish, in high resources language, right? They do answer, but their answers are not great. But that's not the only thing. These models are, they have this closed, these are closed models. We do not know what kind of architecture they are being used. Also, the data set that has been used to train these models, they are not public. So these models are very, there's a restriction to access these models, right? And also these models are restricted to very limited amount of, limited number of non-English languages. So by last month, the ChatGPT 4, it released that its evaluation was only in 26 of the other languages than non-English, right? So that means that they haven't performed evaluation in more than 26 languages, and there are at least 131 languages that Google Translators provide, and there are so many other non-resources languages as well, and we do not know how ChatGPT actually perform in those languages. So these are basically in terms of the proprietary model. So let's take a look into open source model, right? So Guanaco, it was one of the state-of-the-art model. So it's a 33 billion parameter model. So what I'm doing here is I'm asking it to perform a small question answering in Spanish, and we can see that the model is performing well. But as soon as I ask this question over here in terms of Nepalese or in terms of in Hindi, so the model don't even complete the whole answer. So it was a, yes.
How do you know that the model is performing well in Spanish?
Oh, I translated that.
Well, that's just one example, and that's based on the translation of another model, which may have made up for the mistakes in the languages. Are there benchmarks, are there metrics for how well Monaco does?
No, there is not. So these are based on a preliminary experiment that I did. So I'm just feeding them question and see whether it can answer them correctly or not. So what I'm trying to show over here is that Guanaco quite understand Spanish because it's a high resource language, and how the same model fails. They don't even complete the answers in low resource languages such as Nepalese. Even Hindi being the high resource language, don't complete the overall answers. So this was one of the this is one of the high billion parameter model, 33 billion parameter model, right? It was trained on the Llama 33, Llama 30V Llama 30 billion parameter model. But there are few models that have been specifically trained, and they are specifically trained for the multilingualism, right? And they have been open source. We have Bloom, that was trained, that is 176 billion parameter model. So it was trained with 46 different natural languages. Similar to that, we have Bactrian model, which was instruction tuned around another 56 languages. We also have Polyglot 13B model, which was pre-trained with non-English tokens, right? But the problem with these models is that the performance evaluation in this model is not available in a specific language. So we really don't know how these models perform in languages other than the English. The other challenge over here is that few of the models are not being trained in the low resource languages such as Bloom, Polyglot. They're not trained in the low resource languages such as Nepalese or Sanskrit. Also, it's quite difficult to replicate the work of these models. So those were the few challenges. And in addition to that, there are more challenges in creating the multilingual models. The very first one is the lack of data set in non-English language, right? So the first thing is that we don't have the proper data set to train or pre-train these models. And the second challenge is that it will be very computationally expensive, or if you think about pre-training these models from the scratch, or even to fine-tune these models, because they will require a large amount of time, and you also need a very high spec GPU to even to fine-tune them. And there's also another challenge. Even if you train the model, we do not have the evaluation metrics to perform basically to evaluate those models. So we have something called MMLU, Massive Multilingual Task Evaluation, Task Understanding Evaluation Metrics for the English. Even the OpenAI actually translate them to other languages to perform the evaluation of the non-English language, right? So there's another challenge because of the lacking with the evaluation metrics. And there also exists something called curse of multilingualism. So it states that as the number of languages increases, the performance in low resource languages decreases in that particular model, right? So if we look into the curse of multilingualism, and if we go back into these models, then that means all of these models might be suffering from the curse of multilingualism. Yes.
I'm sorry, but this is very interesting. Is this a theoretical result or an experiment?
It's an experimental result.
And performance in which tasks all across the board?
So I don't actually remember which exact tasks, but it's from the Quinu et al. 2019 paper where they performed the experimental analysis, and so it is basically coming from the empirical analysis that they did in the XLMR. I think that's the model that they have been using.
And it's all based on pre-train, not pre-train and then fine-tune.
No, this is based on pre-training and performing it in the downstream task.
Thank you.
Okay, thank you. Okay, so now we have so many challenges, right? In order to create a multilingual model. So how can we efficiently create multilingual model? So there are three important concepts that I would like to introduce first, and then we'll come to the solution. So the very first one is instruction tuning. So instruction tuning, it's very similar to fine tune. So, but what you do here is you add more and more generic tasks, such as classification, question answering in the model, and you train them by providing the context, or it could be question answer prayer, and you simply instruction tune them. So it's very similar to fine tune. right? So when you do that, model can evaluate even in the on syntax, such as given here. You can ask the question for it, and it can give you the answer. The second concept over here is the paved LoRa. So paved means parameter efficient fine tuning. That is basically a library that allows you to further train your pre-trained model. Now, why are we very interested in this? Is because when we use paved, and the LoRa is kind of a paved. That means LoRa means low rank adaptation, which is an efficient way of fine tuning this model. So why it's efficient? So when we use these paved LoRa, we do not need to fine tune the whole model. Let's take an example of 33 billion parameter model. Now, if you want to fine tune that using paved LoRa, what we need to do, we need to add some more adapter in that model, and we'll be simply fine tuning that adapter. We're not going to touch that 30 billion parameters. We're going to freeze that, and we're going to add a few additional layer in the attention layer using lowering adaptation, and we're just going to fine tune that particular extra adapters only. So now, if you have like if you have 30 billion parameter model and you add the paved LoRa, you'll be only training, or you'll be only fine tuning a few millions parameters only. So you don't have to back propagate all the way, right? You will be only back propagating to that additional matrices only. So that's how the LoRa adaptation works. So, and now what this allows us to do is this allows us to fine tune a very large model in a single GPU as well. So we can perform fine tuning in even the large language models, such as 30 billion Llama model, and we do not have to worry about the computation. And it also makes everything much more faster, because now your whole training time reduces from 1 week to few hours, maybe 24 hours or 26 hours, right? So from 1 week to reduction in that computation time as well. The other best thing about LoRa is that you can use the same base model and you can keep changing the adapters. So let's say you train one adapter for the Nepalese language, you can train another adapter just for the Persian language and another adapter just for the other language. So if you want to combine the model, you can do that as well. So you can take the base model and now you attach that adapter. Let's say you attach the Persian language adapter over there. Now you have a 30 billion parameter plus some million parameters model in Persian, and you have a whole single model. You can attach one adapter just after another adapter, and you can perform different downstream tasks. So that's concept 2. So we have instruction tuning, we have paved LoRa, and another concept is the chain of thought. So chain of thought is basically a kind of a prompt engineering. So what we do here is we, instead of asking a question directly to the large language model, such as we gave it some mathematical question, says, okay, Roger has 5 tennis balls, he buys 2 more cans of tennis balls, each can has 3 tennis, how many tennis balls does it have now, right? So we actually give that to the model, and it might answer wrong over there, right? Because it's very, large language models are not that good at doing the math or doing the reasoning task. So what we do is we modify that by asking it to perform the same tasks in a step-by-step way. And that actually works, right? So you can ask the model, please explain how large language models can help us to preserve low resource language. And all you need to do at the end is to append a line telling it, okay, please break down the answer step by step. So that's what we call chain of thought. It's basically a process which we use to tell the large language model to break down the answer in a step by step, right? So now we have three concepts. So the very first concept, instruction tuning. Second concept is paved LoRa, and third concept is chain of thought. So we use that concept to create our new approach called TACO. That means translation in a chain of thought process. So we introduce this method called TACO for instruction tuning LLMs to learn new languages. So what we do is we use the chain of thought. Now we're breaking down the overall process. We use the chain of thought basically to teach the model to learn, to first translate the given instruction in low resource language to in English. Then we teach the model to give the response to that English, and again translate back the response generated in English back to the low resource language, right? Now, there's one more thing that we do. We use curriculum learning strategy. So what that means is basically we are not fine-tuning the base Llama model, but we are fine-tuning a model called Guanaco 33B, which already has been fine-tuned to answer in English language. So it's one of the state-of-the-art model that has done really well in English language. So we're basically now training a model that already knows how to answer, and we're fine-tuning it or instruction tuning it just to perform the taco approach to answer to provide the answer in the non-English language. That's what we're doing. So how does that look like? So this is a sample of the data set. So what we do is we first translate the alpaca 52 and $15K instruction pair data sets. And then what we do, we change it to basically modify it to adapt to the taco approach. So first we provide the instruction. This could be the instruction explain AI to me in Nepalese, or basically writing in Nepalese, exact in Nepalese, or in other low resource language. Then the input is also in the non-English language. So in the output, how we construct that is, this is what we're basically now asking our model to learn. So the first thing that it does is it's actually convert that instruction in that particular language back to in English. Then it provides the response in English, and it again learns to translate this response back into that given language, right? So this is what our data set looks like. So we use this instruction pair. This is also this is same instruction pair. So this is the instruction, and you have the output over here, all right? But here you have to note that we're not translating this input. We're simply if you look here, we're simply translating instruction only and the response only. That input is still fed to the model. The reason that we don't translate that is we want to encourage the model to learn how to make use of that input in the native language. So that's how the data set is. So what we do, we actually perform the training in 3 languages: Nepalese, Sanskrit, Hindi. Those 3 are low resource language, and there's a one high resource language version that we used. So as I mentioned earlier, we use curriculum learning strategy. So all we're doing is fine-tuning on the top of the Guanaco 33 billion parameter model, which has already been fine-tuned, right? And we basically perform LoRa here for the training, and we target the Q, K, and B and O. So query key values and the output projections here. These are the hyperparameter. So we also perform the, so we kept the LoRa R at the 32. That is basically the rank of the updated matrices. And alpha is basically the scaling factor for the LoRa. So the lower this is, the smaller the compressed the model will be. If you keep on increasing them, it will be much more high. You're basically adding more and more layers at the end of your base model, right? So those are the hyperparameters. Yes.
Attention.
I do not exactly know. Guanaco, that's how they pronounce it.
Guanaco. I'm sorry, I used to pronounce it Guanaco.
Maybe I might be pronouncing it wrong.
You're right. You're right. It has multiple attention.
Yes, yes.
When you say Q, K, and B projections, are you referring to projections of multiple Q, K, B's for different attention heads?
Yes. Yeah, I think yeah.
Are we talking about multiple Q, K, B projections?
I think it's a single QKV of projection, and you perform the attention multiple times. I'm not entirely sure if it's the
when you apply attention, when you have multiple attention, you kind of have to have multiple QK. Is that right?
I'm not entirely sure on that.
All right, but
I can get back to you on that one. Okay, so let's begin. So now, if you look into the training, this is the training curve that we have for 4 different models. So in addition to that, for taco method, we also train 2 more models. So we simply train Nepalese 33 billion parameter model and Persian 33 billion parameter model, but we do not apply taco approach here. We're just going to instruction tune them. That means their question is in Nepalese, answer is in Nepalese. Their question is in Persian, answer is in Persian, right? over here, these are for the taco model. So as you can see there, Nepalese actually is decreasing all the way, right? And you can see that all of them are actually performing well. The loss keeps on increasing over the steps, right? Now, after the training, we evaluated one of the, we generated the response in Nepalese 33 billion parameter model. So this is how the output looks like. So after you train the taco model, the system prompt will be in English. The reason for that is that we are performing the curriculum learning here, and we do have that Guanaco model that understands English well, right? So system prompt will leave that in the English so that model understands it well. Now we provide the instruction in the native language or in the low resource language. So the response from the model is first translate that in English. So that is basically saying 5 वर्षको बच्चालाई inflation बुझाउनुस्. So that means like explain the concept of inflation to a 5-year-old, right? So now if you look here, you have the response in English where the model performs that response in a satisfactory way, and it translates that back to the response in Nepalese in a very nice way. We did the same one in the instruction tune model where the model starts to hallucinate and give some very non-factual results. So now that we have the response generating from the model, now we need to evaluate how good our model is, right? Now the problem here is that when you think about evaluation of LLMs, now things becomes very challenging. How do you evaluate the LLMs, right? If you remember the one of the challenge I mentioned, we don't have that evaluation benchmark to perform in multilingual settings. So what we can do here is we can incorporate a human over here and ask them to evaluate, but you might have 20,000, 30,000 responses to evaluate, and that becomes very costly. Also, when you have humans over in the evaluation, now the judgment becomes more biased. So what can we do, right? So what we can do is we can actually make use of the existing state-of-the-art models such as ChatGPT-4 to perform the evaluation, the response that we got from our model. And this is the approach from Chiang et al. Chiang et al. So what the authors did, they come up with the Vicuna benchmark to evaluate the open source model called Vicuna. And it consists of 80 different kinds of questions, right? And they are in 9 different categories, from generic, knowledge, role play, common sense, Fermi, counterfactual, coding, math, and writing as well. So what we did, we translated these Vicuna benchmark using Google Translate to the languages that we require them for. And then we use our taco models and basically follow the single answer evaluation. That means we're asking ChatGPT just to evaluate our answer and nothing to, and we're not giving some other answers to compare. So basically we do that. And then we also need to make sure that our evaluation prompt should be good. So the evaluation prompt looks like this, where we are basically asking our model, our ChatGPT model right now, GPT-4, to be an impartial judge and evaluate the quality of the response provided by an AI assistant in the language, in Nepalese, to the question displayed below. So the questions will be appearing over here. You can see that it also asks the evaluation should consider the helpfulness, relevance, accuracy, depth, creativity, and the level of the detail of the response. And we add one more line over here. We ask the model to do not allow the length of the response to influence your evaluation, right? So why we do that is because of the token limit of our models. So our models is first performing in the first, you pass the question in non-English language, then it translate it into English, give the response in English, and we translate back. So in that process, it's consuming a large amount of token, right? And it will exceed the token limits. So what we do at the time of the inference is we add one more line in our instruction saying that the response of the model should be in 6 sentences. So that will make sure the answer provided by our model do not exceed 6 sentences. That means we can have the response in English, and we can also have the response in the non-English languages, right? So when we do that, we simply compensate for that in our evaluation by asking the model by not to allow the length of the response to influence your evaluation, right? And then model, basically ChatGPT model gives us the rating from the range of 1 all the way to range of 10. And it also gives the short explanation like why it gives exactly that rating to that answer. So that basically our evaluation. So now we are evaluating the model that we have created using the ChatGPT 4. Now, when we do that, we can see that in each category, we have results for each of the languages. So over here, if you look here, we have an average of 8.2. So basically, we have 82% overall in terms of the score. So I do have the graph representation for this. Now, if you remember, we also trained two models for our evaluation study where we did not apply taco approach. So these are basically instruction tune model, these two of them. So we are simply training them in English, in the non-English language, right? That means instruction is in Persian, output is in Persian. Instruction is in Nepalese, output is in Nepalese, right? And over here, you can see all those models that we have applied taco approach, right? So if you see there, there's only one in which we have Sanskrit math where the model performs really bad. Other than that, our approach shows that we are doing really great rather than simply instruction tuning our models, right? So all of those models, 4 models, are performing at a very high level. So over there, you can see that this knowledge, and you can see that all these 4 of them are quite high. And I want to focus on the knowledge because now it makes the model quite factual than it was before over here. So this proves that our taco models is working well rather than simply instruction tuning the model. So we do have a state of, so these are now the discussion that I have. I would like to focus on a few of the points. So the very first one is that we are the SOTA models written in English language, English language only. They cannot generate the responses in the language that it has not seen. What I meant by that is, so the base models, if they are lacking, if they have not seen the language, such as Sanskrit language during the pre-training, we cannot simply find or instruction tune them or fine tune them to generate the responses in the Sanskrit, right? Because the model might not have seen that answer at all or does not know that particular concept at all. There comes the emergent capabilities, but even that has some limitation to that. That's why when you look into the previous chart, you see that knowledge is quite less in Nepalese languages, and also it will be less in the other languages as well. The second point is that pre-training the model in a non-English language is very expensive, as I mentioned before, and also very challenging due to the lack of available data set. So what can we do? We can actually make use of curriculum strategy where you use the existing state-of-the-art models such as guanaco 33B, and then train on the top of that. When we do that, we don't have to train a model from scratch for English tasks, right? We can save a lots of computation tasks, and it will also save lots of cost associated with that. So the concept behind the curriculum strategy is to basically start with the basic principles and then gradually progress towards a more complicated one, right? Here also, we are doing the same thing. So our model is basically understanding, it already understands the guanaco 33B parameter model, already understand how to answer in English, right? So we don't have to teach that model how to answer in English. All we need to teach them is how to answer in the non-English or in the low-risk language. And that's what we did with our taco model. So the question is, why does taco approach work, right? So here we are teaching a model how to answer in non-English language, right? But the model already knows how to answer in English language. Now we have two hypotheses with two regions. The very first one is that because it works because of the emergent capabilities with an increase in size, right? So we tried in our preliminary experiment with the 7 billion parameter model where this approach did not work. But the same model actually works with the 33 billion parameter model. And the second reason is the chain of thought prompting. Right? When we do the chain of thought prompting, it elicits the reasoning behavior in the model that has been shown before in the chain of thought paper as well, where you can solve the complex tasks by breaking it down into a number of steps. So the advantage of taco approach is that it utilizes the pre-training knowledge from the English languages and basically leverage that to generate response in the non-English language, right? So why this work is because now the model needs to scan its parameter from the factual information that it has learned in the English, and it basically avoids the hallucination. Because when we use the Taco approach, for every question we give it to the model, it's actually translate that into the English and it starts searching in its English parameters, right? So that's why you have the more factual information, and it avoids the hallucination on that. But we haven't done the hallucination test. I'm talking hallucination in terms of the score that we have observed from the knowledge. So we observe, and that's what we have here. So in average, we have 92% accuracy in the knowledge category across all 4 languages. But there are many limitations to this approach, right? So the very first limitation is because of the token generation. So the model needs to generate answer in both languages, in English, also in non-English. So the number of tokens required often exceeds the maximum token limit of the base model, right? So that's one of the challenge. So because of that, if you trying to ask it a very linear question, right, or summarize a document, then the model might fail in those cases because it will prevent the model from providing the lengthy responses. The second limitation is that our model is answering everything in perspective of the English language, right? So basically the model is performing suboptimally here, and it fails to capture the creative writing such as poems or rhyming sentences. Because now you ask the model to create a rhyming poem in Nepalese, but the model will translate that into English and it looks into the answer in terms of the English. So that's the another limitation, right? So 2 significant challenges associated with the multilinguality: token counts and time required for response generation. We do have the limitation of the token itself, but I want to emphasize on these 2 as well, because the number of tokens needed to generate a single sentence in non-English is going to be much larger than in English. And because of that, the more tokens you have to generate, more time it will take. So when you have more time taking model, your cost will also be quite large, right? So here is an example where we have a sentence here regarding AI, and this is using the tokenizer of ChatGPT tokenizer, right? So yeah, you can see that overall token here is 55 only for that paragraph, and over here you have 229 tokens written in the Persian. So if I change this to Nepalese, it was 253 or so tokens in Nepalese as well. So in many of the languages, especially in low resources languages, where you have a text in non-English, the token counts usually increases. And you can say it's not only double, it's more than, it's 4 times, or it's around 4 times. So now when you do that, right, and when you have non-English languages in the generation, it will take more time. So we did a preliminary, we did some analysis in our as well. So what we did, we simply asked the instruction tune model to generate the answer in English over here, right? For first 6 questions, and then we asked each of our model using the Taco method to generate that, right? So we can think, all right, so Taco models are generating 2 answers in a very simple way, but this is generating a single answer. So even if you double this here, right, you can look into all those answers generated by the models are way higher. It's taking way too much time than it's taking in English, right? So that's another limitation of the model. It takes a longer period of time to generate the responses. So if you have a linear question answering, it will take more time. So that's also another limitation of the model. So in conclusion, we introduced a new approach called TACO, translation in chain of thought, which we utilizes to create an efficient multilingual model. We show that our TACO method impresses ChatGPT-4 by achieving 82% on average on the Vicuna dataset. Our results demonstrate that we can use TACO that can be used effectively to generate a multilingual model at a very reasonable cost, because the cost now decreases. You don't have to fine-tune the whole 30 billion model. All you need to do is adapt the LoRa approach here. We want to acknowledge that we have not done the robustness or toxicity test in our model, so model might perform the harmful content. So based on the challenges and the limitation, we are going to focus on these future works. The very first one is to achieve the better results with the smaller size models, such as 7 billion parameter model. We also want to increase the context window to solve the tokenization token limitation. We can use new methods such as fast transformer or or polytech transformers for the increasing the context size of the context size in our model. And we also want to perform the robustness and toxicity test to create the safe model. That's our future work. I do have few examples taken from the model here. So this is the very first example from Taco Persian 33 billion parameter model, where I asked the question, what would have happened if Alan Turing had not cracked the Enigma code during World War II, right? So, okay, so the translation is, sorry.
The translation for
So I think I'm using, I'm using Google Translation. So
that's a Google translation of that.
Yeah.
Right.
I'm not sure what that is. Is it, what is it?
That's syntactically
Okay.
The verb form that's used in correct. But regardless, that's still a valid example.
And as you can see that you have instruction in English and its response in English, and again translated back to the response in Persian. The second example is write something that is controversial in less than 5 sentences, right? Where it talks about a legalization of marijuana, and again translated back into Persian, right? So those two are the examples, and I have another examples, a very useful one on how to impress your wife. So the answer is ask your model to write a poem for it. So it actually write a nice poem, right? Now, coming back to the one that where models lacks the creativity, you can see the example here. In Nepalese, it does not write, right? But, and this is from instruction tune model, not even from Taka model. Even in the instruction tune model, the model is writing in the perspective of the English, where you see the things rhyming together, each other, all together, right? In terms of the English, but not in Nepalese. It's a good poem, right? If you're a good poet, you can make it, you can sing it in a nice way. But when I start to analyze this one, it seems like model is still, even in instruction tune model, the model is talking in terms of the, in the perspective of the English language, right? So that's the reference, and that's pretty much about it. Thank you so much for listening. If you have any question, please feel free to ask. Thank you.
Wonderful job. I'm going to abuse my powers again. So we can see. First of all, Vivek, you might want to mention that the models that you mentioned are already on plugin phase. Are they available to the public?
I need to make it public.
Yeah, that's just a couple of things.
Okay.
So, the Vicuna benchmark is comprised of 80 plus the first 2 layers, the tokenizer, and then the embedding on top of it. That would essentially bring English and low resource language to the same level of symbolic representation, which means that the higher the attention goes, the same level of context. What do you think about that?
We need to give it a try. That's what I'll think, because so when I was going through this poem, right, that's when I recognized that, okay, so I knew that it was a writing. If you're using the Taka approach, it's very clear that you're looking into the answer from the perspective of English language, right? But this was simply instruction tune model. So this all is basically coming from that. This all is basically coming from the when you perform the instruction tuning, right? But when you look into its translation back into English, it seems that it's basically understand to in its own parameter just to write down in English and then translate it, right? I think it's somewhere within its abilities simply performing that, even without the Taka approach. So when I looked into that, I thought, okay, maybe it hasn't learned a lot what the poem means in that native language. So I think whether it could come from the free training, right? Or it could come from training a large tokenizer as well. Or you can have embedding model and then send it to that model. It could come from there as well. Or the other alternative could be the fine tuning or instruction tuning in that creative work.
That's beautiful. I actually have a counter argument for that, but I'm going to leave it until after other questions are answered. Nancy, do you want to follow up on that?
Yeah, so let me give you an example. If you gave an LLM a prompt, let's say a story, you ask what's the moral of the story? Apparently in some languages, the moral can change. Like in those particular settings, obviously, if it's translated to English first, English perspective of the answer itself might be skewing the model to answer the way the English person answered rather than something that native language. How would you go about addressing some of that bias that might inherently leak into that model? Because I think it's not just, right, the translation model that you're also interested in, but also the things that surround the language in terms of the uniqueness to what constitutes the language itself that might be of interest to preserve and
Yeah. So, okay. So you're basically saying that model could be biased in one language and it could not be in the English, right? So what can we do about that, correct? So right now, I don't have the exact answer on how to work on that because that's one of the this is a question that I have to look into, right? Okay, so the way that I look into it, and I'm going to give you an example of the OpenAI, right? So OpenAI does not employ a single model. There are a mixture of models that works all together, right? They have this very closed architecture that they have that we have no idea about how it works, but it works in a good way. So they understand. Let's forget about the low resource language. Let's talk about even the Spanish one. So they might have different models that working together, right? So when you ask a question to model A and the model A generates the answer, there might be model B actually doing the factual check on model B that generated response, and then try to prevent that answer and again ask the model to create another answer. So that's one way to prevent those biases in the generation, right? So basically you use the mixture of experts, that's what they call them. They use a mixture of experts model to basically counter those harmful responses or those biased responses. There's something called multilingual adaptive tag. So when you tag a large language model, right? So in OpenAI, ChatGPT as well, it has been attacked. So all you do is you ask the harmful responses in the low resource language. So you ask them how to create some, how to destroy the word, and you ask it in the Nepalese or Sanskrit language, and model will give you the whole answer, right? Because it hasn't been trained to avoid the harmful responses in the low resource language, right? So it doesn't understand. So it just generate the response. Does that answer the question? Okay.
One question. You started off your presentation with Sanskrit, right? As a low resource.
Yes.
language.
Yeah.
So, is Sanskrit really comes under low resource language, or it is like nearly like it doesn't have any kind of existence on because these models are trained from online resources or write-ups or available to them, right? So there are Sanskrit is an extreme case, right?
Yeah. So Sanskrit is a low resource language, right? It has been classified as a low resource language, right? So how we train is we use the translator, Google Translate, to first translate the data set that we have in English to Sanskrit. So now we have the resources to train the model in Sanskrit. But the base model that we trained on, it's a Guanaco model that is also trained on Llama 30 billion parameter model, right? So it was specifically trained in the English setting only. So what we do is the translated data set that we have in Sanskrit, now we use that to train that Guanaco model. And so the performance that you're looking into Sanskrit is coming from that model.
Yeah, that I understand, but along with Sanskrit, you also take Nepali that time?
Yes.
Or Maithili?
Yeah.
So still some amount of information or write-ups are available on Maithili or Nepali online, but Sanskrit is kind of a dead one. It is too extreme case to pick.
Yeah, no. So I got you, but you're trying to say that many people English, Nepalese, or Hindi, or Maithili than Sanskrit. Sanskrit is like not that spoken, right?
Or
but,
written.
Yeah. No, Sanskrit is written. Like
type.
No. So they are low. They are already all three of them. They categorize under low resource language, right? There might exist resources on them, but just because we have the written text doesn't mean we can use them to train the model, right? So that's the problem with lack of availability of the data set. That's why you translate the instruction pair of the AlphaGa 52K and Dolly 15K to the Sanskrit to create our own data set so that we can train our model.
Also, this process, the one you
Taco approach.
Taco approach, like converting to English and then answering it and then translating back to the language. Like there was a parallel thing which happened, like while learning to speak in English, we were advised to think in English.
Yeah.
Like many of us are advised to think in English. Like we translate to our mother tongue, then we answer in that mother tongue and then translate back to English.
Yep.
So you are also just reversing that thing.
Yes, and I think you catch exact same thing that I wanted to say in this slide. So where did it go? So I mentioned that exact same thing in our discussion and the paper as well. So that's what we have in the TALC approach, right? So in addition to that, we also have the curriculum strategy. That means you start with the basic thing, and then you eventually go to the challenging stuff. So in the TALC approach, we can think of a basic stuff as a so curriculum strategy is kind of like you start in a basic and you simply go towards the complex one, right? So the basic stuff or the basic thing to do here is to first learn how to answer stuff, right? So that's what Guanaco is. So it learns to answer in English. That part is done. Now the complex portion is to train it how to speak or how to respond in the non-English language, right? And that's what we train with the TALC approach in that model. Now it's capable of actually answering non-English. What you missed, I wrote the exact same thing in our discussion. Yeah, that's how we do it, right?
So, let me play the devil's advocate. If this is the wrong thing to do, why do it?
I'm not saying it's the wrong thing to do.
The ideal thing to do would be to think in the same language as we're asking the question and expect to see the response for it. Why is this worth doing?
It's very efficient and it will save you a lot of compute. That means in terms of the cost, and so it will save you from pre-training your whole model, right? That's like saving you.
I wanted to pre-train my whole model on Panther. How much data is available?
You can get the data from Common Crawl, but I don't think that will be enough for you to train even a billion parameter model.
Exactly the point. It's not great, but it's something.
Yeah, but it works. That I will say that it's not great, but it works, right? So what you can do, you can if you can deploy the same model in the speed of ChatGPT, and you can perform, if you can solve that token limitation with a long transformer or hyper attention, right? You have a solid model that will talk to you in the native language.
Is the token problem solved with hyperattention? Or
It will increase the context windows also in the response.
The tokenizer.
I don't know.
The tokenization is a deterministic process based on the corpus that you have, white curve or sentences and so on.
Yes, but when you change the tokenizer, you also need to change your pre-trained model, correct? But now you're talking about pre-training the whole thing. The base model that you have, the base model you have right now in this approach is in English. If you use the new tokenizer and you include the non-English language in the tokenizer, that might not be the best approach there, right? Because you train the model using the previous tokenizer. Compared to your base model, your tokenizer will be different.
I understand your tokenizer will be different, and you're saying that if you change the tokenizer and then start feeding in new token IDs or new meanings for token IDs, use a model and continue training, it's not the best approach, right? And I see what you're saying. What I don't understand is best approach compared to what? What are the other?
Pre-training from scratch, not only the
training from scratch. Well, you don't have published.
We don't have.
Right.
Yep.
That's not a great idea. This isn't the ideal thing to do. But that may actually, I'm sorry for
no, that's
but I just wanted to point out that if you're going all the way down to changing the attention mechanism, you're already proposing a new pre-training process from scratch.
Yes.
If you want to go down that path, why don't you do the cheaper thing?
So you have a base model here, right? Right. Now you have a tokenizer here, right? So when you're pre-training, you're basically using everything from this tokenizer, correct? So your base model already knows tokenizer A. Now you're using the same base model, right? With a different tokenizer. Now, tokenizer is basically the changing of code.
I understand what you're saying, and you understand what I'm saying. your alternative was, when you started, that discussion, was maybe, loop attention or, long transformer would be a solution to that one. If you want to use those solutions, aren't you starting the pre-training process from scratch or changing?
No, we're not. We're including that in the existing transformer. That's what we do. So it's I forgot which paper it was. You can simply add those fast transformer in the lower apples only. You don't have to do everything in the pre-train.
Maybe I have an incorrect perception of what you're referring.
No, I got, now I meant what you said, but when you said like changing the attention mechanism, we might want to change it here. Then why not change the whole tokenizer, right?
You are adding a few more units of self-attention, feed forward output, but of a different type with different.
So there are two papers. One was used in GPT-2, where I think they changed the whole architecture of GPT-2. In that case, yes, we can change the whole tokenizer, right? So there was another paper which includes this.
Did they change the tokenizer or did they change the?
Oh, no, we can, I'm saying that we can change the tokenizer. That's what I'm saying. If we're pre-training it from scratch, changing the tokenizer seems a very good way. That I would say that's one of the best way as well. But if we're stuck with the current model and we're not changing this model at all, then I think that if we change the tokenizer, it will also change so many things over there, because the simple text might not be the same because the encoding will change after that.
See what you're saying. If you are training for the downstream task of spam classification and you start from a language model, language modeling is a different task from spam classification, right? You end up updating quite a few ways in the back propagation process. But you end up converging relatively quickly.
Yes.
Isn't there a case to be made for changing the tokenizer and still saving on the number of training steps required to converge compared to starting from scratch?
And now I have follow-up question. Are you using the same base classifier? I just want to change the tokenizer.
Yeah.
Okay, now here's the thing. So when you encode that simple language, right? Without Nepalese or Sanskrit, it will give you one encoding.
Yeah.
As soon as you add the other language, it might give you the different encoding even for the English. So this model, right, that has been.
When you say encoding, are you
I'm
referring to the IDs of the token?
Yes, that's what I meant.
As in the tokenizer gets updated?
When you're changing the tokenizer, it will be updated, right?
When you change the tokenizer, you're changing the token, which means you are also changing the vocabulary.
And you'll change the IDs, right? At the end of the encoding IDs. Yes.
Right, that's what it means. But when you add a new language,
yes,
the way you do, that doesn't change.
No, the way that I'm doing it's not changing.
Now, what you're telling me is that, let's say we have transformerify. Previously, transformer got its own ID, if I got its own ID, right? Those are the subwords in your vocabulary, in the part of language, right?
Yeah.
What I'm telling you is, supplement that vocabulary so that transformerify would also get it. I'm not saying that you're replacing.
Oh, it will get the same idea as before?
No. You remember byte-pair encoding, right?
I am, but so
subword.
Okay.
In subword encoding, you start your vocabulary with characters, and then you add to that. You check and see which two words are next to each other, which two tokens typically appear next to each other, and you keep building them. What I'm telling you is do the same, extend the vocabulary. You aren't replacing the meaning of subword, but you are adding new ways of representing.
Okay, so I will go for the extending part, because now in the same tokenizer, you're adding new languages, right? And so the only case that I want to make here is that the English text that goes from here their token ID should be the same that goes over here.
Yeah.
Right? And that's what I meant. So if we simply change the tokenizer, that English coding might also
Right,
get
I see what you mean. No, there was a miscommunication.
yes.
Changing the tokenizer in my suggestion means extending the channel.
Okay, so if you extend that, then it won't be that issue, right? Because it will still understand the English token IDs.
Yeah.
So when you change it completely, then that might be the issue. That's what I meant. So extending it, I think, yeah, that might work. But it also, we need to make sure that the A is preserved here with all those English, and you're just adding the new languages for new token IDs.
I'm sorry that this took so long and we are already.
Bahar, you had a question, sorry.
So your contact model, LLM and translation machine.
No. So I am doing this. So I have a base model, all right, 33 billion parameter model. So I add adapter here, okay. I add adapter here like this. Sorry, it should be big. So this is a small adapter. So this is 33 billion parameter model. This might be in millions only. So all I'm doing is I'm frozen the weights for this one. So when I back propagate, I'm simply training this one. I do not train this, right? So all I need to do is I need to fine tune the model using million parameters only. And the way that I'm fine tuning is that it learns to generate. It learns to generate exactly from here to here. That whole is its output. So your input is only this. This whole is your output. Sorry, that's an input. I can show you in here, right? So your input is only this, and this is what you train the model. So when you give this as an input, your model should learn how to do this all the way to this. So translation is within the output itself. Right?
And
Yeah.
the data set that you are training is
I create the exact same data set. So our data set look exactly same. You get that input and output is like this. Yes. It's called Vicuna benchmark. Yes. Yes, it's going to work. So if you look into the, if you look in the evaluation, right, it works quite well, but it's not best, right? And this is something that I mentioned in the paper as well. It doesn't make that sense if you want the model to code in non-English language, right? Because that's not the conventional approach. So if you look into the coding here, right, it's not that good. It's perhaps good in, I think it's Nepali 33B. And what is the other one? Oh, sorry.
It's an example of a coding task.
It's write a Python code for this, write a Python code for that. So those are the coding tasks. No, it's both in English as well as in the native language as well. Yeah. So the way that it will write is basically it replaces each keywords that it thinks of. First it's write in English, and then it translates those variables. And that's why I think that's why it got that much scores. I've seen that, and I write in the paper the exact same thing, that is very unconventional to evaluate the model in terms of their coding skills in non-English language. Because coding is always in, you usually, it's a coding, right? So you use the coding language.
So is it essentially evaluating using or evaluating the English description of what the code does?
No, it's evaluating the whole coding itself in that particular language. Yeah. So it's not only going, it's basically going to look into, does that make sense or not? So it's not getting the perfect score. You can see that it's less than, many of them are less than 8. None of them got the 8.
So this is something that we need to look into.
Yep.
Thank you.
Is it okay if I stop the recording?
Is anyone still online?
Yes. Kiran is there. No questions so far.
Let's stop the recording.